The objective of today's lecture is to use the core principles of mass balance and flow down gradients to predict how a feed-forward increase in sympathetic nervous activity protects arterial blood pressure and supports enhanced exercising muscle blood flow during the transition from rest to large muscle mass exercise. To begin, here I have drawn a simplistic physiological model of the circulatory system. We will start by creating our mass balance model, starting with our regulated mass, which is blood pressure in the arteries. Inflow to the arterial compartment is cardiac output, where cardiac output is dependent on a high pressure created by the pumping of blood by the heart, arterial blood pressure as the low pressure, and the aortic valve as the conductance. Outflow from arterial blood pressure is blood flow to all tissues within the human body. This flow is dependent on arterial blood pressure as the high pressure, venous blood pressure as the low pressure, and conductance is dependent on how dilated arterioles are throughout the entire body. At rest, inflow and outflow of blood from the arteries is balanced, therefore arterial blood pressure is stable. At the onset of exercise, there is an increase in motor drive. This motor drive leads to an increase in muscle contractions, leading to an increase in metabolites, vasodilators, as well as compression of the arterioles. Combined, this contributes to a rapid vasodilation of the exercising muscle arterioles, leading to an increase in vascular conductance in the exercising muscle. This is depicted here by an increase in arterial dilation, leading to an increase in the conductance for outflow from arterial blood pressure. Therefore, outflow increases, leading to an immediate drop in arterial blood pressure. Because outflow exceeds inflow, there is a drop in mean arterial blood pressure. Exercise therefore reflects a challenge to arterial blood pressure. Luckily, our brilliant bodies have feed-forward mechanisms in place to help protect arterial blood pressure and support exercising muscle blood flow during exercise. With the onset of exercise, the motor signal sent to the exercising muscle simultaneously leads to an increase in sympathetic nervous activity. The increase in sympathetic nervous activity leads to an increase in heart contractility, leading to increased volume of blood ejected per heartbeat, as well as increased heart rate. Therefore, there is more blood being pumped by the heart more frequently, leading to an increase in the high pressure for flow of blood into the arteries, contributing to increased arterial blood pressure. This same increase in sympathetic nervous activity leads to an increase in vasoconstriction of non-exercising tissues, leading to a reduction in vascular conductance, depicted here as a decrease in the diameter of the inactive tissue arterioles. And on our mass balance model, this is reflected as a decrease in conductance for outflow, leading to a decrease in outflow, contributing to arterial blood pressure increase. In the active muscle, there is also an increase in sympathetic nervous activity that could lead to vasoconstriction, leading to a reduction in vascular conductance. However, because of the exercise-related local vasodilators, metabolites, and arterial compression, vasodilatory input exceeds vasoconstrictor drive, leading to a maintained higher exercising muscle vascular conductance, and therefore enhanced exercising muscle blood flow. The increase in outflow from the arterial compartment rapidly leads to an increase in blood volume on the venous side, first in the peripheral veins, then the central veins, and then back to the heart, leading to an increase in inflow back to the arteries, contributing to increased arterial blood pressure. Muscle contractions further enhance return of peripheral blood volume to the heart by compressing veins, increasing venous pressure, and therefore venous return. Simultaneously, unidirectional valves prevent retrograde venous blood flow. The same feed-forward increase in sympathetic nervous activity leads to an increase in venoconstriction, resulting in a reduction in the capacitance or size of the venous compartment, helping to increase venous pressure and therefore flow of blood back to the central veins, then the heart, contributing to increased arterial blood pressure. In summary, following an exercise-mediated decrease in arterial blood pressure, a feed-forward increase in sympathetic nervous activity leads to increased heart contractility and heart rate, leading to increased arterial blood pressure by increasing inflow, increased vasoconstriction of primarily non-exercising tissue, leading to increased arterial blood pressure by decreasing outflow, increased venoconstriction, leading to increased arterial blood pressure by increasing inflow. Combining, the feed-forward mechanisms act to rapidly restore the balance of blood flow into and out of the arterial compartment, helping to protect arterial blood pressure while supporting the high pressure for flow of blood to the exercising muscle. Depending on the magnitude of the feed-forward sympathetic nervous activity increase, arterial blood pressure may already be restored back to resting levels. However, as you might have noticed, none of the mechanisms discussed so far have been in response to a sensed decrease in blood pressure. Therefore, these feed-forward mechanisms may not have been effective in regulating arterial blood pressure. In our next lecture, we will therefore assess how feedback mechanisms contribute to regulating arterial blood pressure while further enhancing exercise muscle blood flow to support the metabolic demand.